So good evening all. So I am Yogendra Narayanan. So I am a research scholar. So today we will be discussing on geological storage of carbon dioxide, especially in deep saline aquifers, which is the topic which I am working on. So as Fakra talked about energy transition, and one aspect was to search for alternate sources of energy. So that is one aspect uh, of tackling the climate change. So second aspect would be what we are going to do with the present scenario. So even though the renewable energy sources are getting a pace in India, so still we are dependent on fossil fuels, and from several hard to abate industries such as steel, chemical factories, thermal power plants, refineries, etc. still use fossil fuels, and they emit large amount of carbon dioxide, which are termed as point sources. So with this, India almost contributes to 7% of total carbon dioxide emissions. So out of this 7%, most of the 90% of these emissions are due to fossil fuels, burning of fossil fuels. So as you can see the graph, in the last almost right from independence, there has been a drastic change. It is largely due to the rapid industrialization post independence, and almost it has increased up to 4000%, as you can see. So in order to tackle that, since India is a large country and we need to tackle this, so most of the ways to tackle has been discussed in COP, which is the International Forum for Climate Change. So recently COP 27 held, and the main findings were not findings, I would say. So main points of discussion were, as far as India is concerned, it will go carbon neutral by 2070. So that was the target. So and mostly it is the mandate for the industries are also like this. So this is from the CIA website, Confederate of Indian Industries. So now how to achieve this? So one thing is moving towards fossil fuels, which will moving away from fossil fuels, which will in future reduce the carbon emissions, and simultaneously we are using fossil fuel based power, and one aspect is removing those carbon dioxide from point sources or from these hard to abate industries and utilizing them or storing them. So and the amount of carbon dioxide which is getting generated or emitted is in a very large scale. So apart from industrial utilization, we need some sink in order to store them permanently, or in order to remove them from the emitting source permanently. So in this aspect, we have sedimentary basins, as Fakra briefly touched upon. So sedimentary basins comprises of depleted oil and gas reservoirs, deep saline aquifers, and coal bed seams. So these come under sedimentary basins, and India has a vast resource of sedimentary basin, and from the slides you can see that almost 33 lakhs square kilometers of sedimentary basins which we have, which can be utilized. So these are highly porous reservoirs, so rock formations which are suitable for storage of various gases. So right now hydrogen is also being considered. So and basalt is a separate formation, those are igneous formations. So those have 97 gigatons. And as far as preliminary estimates are concerned, deep saline aquifers are considered to have a very large storage capacity, and the main issue here is it has not been explored in a large extent. So oil and gas reservoirs have been explored, coal bed seams have been explored, but not deep saline aquifers to such extent. So by tackling this problem, we will be contributing to two sustainable energy goals, which are clean energy in future, and second is climate action. So to get into this, so it will be more of I will not cover much of the policy issues and everything, so it will be relatively technical discussion. So some fundamentals to understand what are sedimentary basins. These are what are deep saline aquifers. So these are part of sedimentary formations, mainly consisting of sandstones, limestones, which are classified as clastic and carbonates. So the reservoir rocks, which are the sink for the storage, are made up of this one. So in order to arrest the injected CO2 from leaking, so we have a term called cap rock, so which are essentially made of shale, which is highly compacted clays, and these formations exist in elevated pressure and temperature conditions, and typical pressure and temperature gradients are given in the slides. So now the next question is, why these formations are considered efficient for storing CO2? That is the major questions which arise next. So here at these pressure temperature conditions, which are at the depth of 800 meters to 3000 meters typically, so carbon dioxide exists in a supercritical state. So supercritical states is typically very and very low viscosity. So it has a gas-like viscosity and a liquid-like density. So what is the advantage of having high density? So you can pack more amount of, as mass can be more in a particular volume. So that is one of the major advantages why these formations are suitable for injection and storage. So these graphs are typically the phase diagram of CO2 and how the density and viscosity varies. So now when we see what is the available literature in this, so first aspect is the major risk associated with this is, it is as a geotechnical engineer, what will be its geomechanical response, right? So how the stress states will vary, how the pore pressures will vary, and how these will in turn affect the reservoir itself, what type of failure will occur, what type of deformations will occur. So in order to understand that, you need to understand what happens when CO2 gets into the system, and what are all the interactions that take place, and due to that interactions, what are the consequences which contributes to the observed geomechanical behavior or the expected geomechanical behavior, and further to approach how to mitigate them. So that is the major goal. So in order to do this, we need to understand at the pore scale level what is happening. So that is what as far as this lab is concerned, we are concentrating on it. Any doubts? So we will see one by one what happens in the system first. So if you are not getting, yes.
These aquifers presently contain some like fluid?
Yeah, those are saturated with brine, highly saline waters. So first of all, we will understand what will be its geomechanical behavior. What happens? So as far as geomechanical behavior is concerned, first what we do is we can consider an idealized situation. So this is how a typical ideal reservoir would look like. So as you can see, the top is overburden, cap rock, reservoir and crystalline basement. So it exists at a pore pressure of U at a temperature T, and initially it is saturated with completely with brine, we are considering it, alright. So and it has a porosity of phi. Right, now what happens is we are these are the terminologies which we use. Now this is the stress state initially. So sigma V and sigma H are the horizontal and vertical stresses that acts on it. Now what happens when CO2 is getting injected? So when CO2 is getting injected, it forms around 4 zones apart from the existing zone, right. So the first zone, usually CO2 is injected at a lower temperature than the formation. So when a lower temperature fluid comes into contact with higher temperature reservoirs, heat exchange occurs and initially the reservoir will cool down, and simultaneously the pressure of injection of CO2 is higher than the reservoir pressure. So the pore pressure existing or the fluid pressure that is existing in the reservoir will rise. So these two combinations will occur in zone 1. Apart from that, there will be a change in saturation. Some pores will be occupied by brine and some pores will be occupied by CO2. So these 3 changes occur, and followed by in zone 2 the temperature effect will be minimized, but the pressure and saturation effect will be there, and in zone 3 it will start, that can be considered a zone where the interface occurs between CO2 and brine. So as time progresses, it is at a particular time during injection, and zone 4 is where the effect of pressure will be visible, but CO2 has not reached to that point, alright. And zone 5 will be the virgin zone, which is not yet disturbed, but it will be as time progresses. So at zone 1 the stress state will be, so there will be an increase in total stress as well as pore pressures, and simultaneously due to cooling the rocks will start to contract. So there will be a reduction in total stress also. There will be an interplay between the variation in stresses. So that is why the increase in stress, there will be both increase and decrease. So the stress state or the failure depends on the magnitude of this increase or magnitude of this change. So and simultaneously in zone 2, 3 and 4 there will be increase in only stresses due to the injection pressure, and finally at zone 5 it will be the initial stage. So you got an idea of what is happening inside? Any doubts? Yeah, so here when the pressure of CO2 when it is injected, it will be at a higher pressure than the existing pore pressure. Now what happens is that during this injection, obviously you can imagine, you can visualize there will be an increase in pore pressure, but since it is a line injection, it is not a point injection, it is a completely, it will be injected as a plug. So there is a effect known as poroelastic effect, so due to which there will be an increase in the total stress also. right. So due to that the total stress varies, and simultaneously in some zones there is cooling occurring. So when the cooling is occurring, that portion of the rock starts to contract. So due to which the the horizontal stresses acting starts to reduce. So this is the interplay that occurs. So this is a perfect example of T, H and M coupling, thermo-hydro-mechanical coupling. So here temperature is changing due to the flow of CO2, which is hydraulic. Due to this combination, the stress state itself is changing. So that is mechanical. So this is THM coupling. Alright. So now from this we can understand the major parameters which are affecting is pore pressures, saturations and temperature, right. So how to detect them? What are all the techniques used for detecting this, and what is the change we can observe from outside? So that is what the next question is, right. Any doubts here? Are you able to follow at least a bit? So now determination of saturation, which is one of the important parameters, which I am aware you are familiar with effective stress equations, at least some of them. Are you introduced to that concept? Yes or no? So effective stress is total stress minus pore water pressure. And there it is pore water pressure, here it is combination of pore water and pore gas. So that depends on saturation also, saturation of the phases that exist in the rock mass. So here how to detect them? So we need to use some techniques which will capture the contrast in some properties. So what is the density of water or brine? What do you think? What is the range? It is around 1000 kilogram per meter cube for pure water at 4 degrees centigrade, and brine, when addition of salts take place, it will be increased. So it varies up to 1200 kilogram per meter cube, right. What is the density of CO2? At least in gas, it is very less, and in supercritical it will be almost it's in its liquid phase density, which is around 600 to 700 kilogram per meter cube. So you have a large density contrast. So if there is a density contrast, what will vary? What elastic property will vary? Its bulk modulus will vary, right, and its elastic modulus will vary. So one of the aspect of detecting this is using acoustic waves, which are compressional and shear waves, right. So these acoustic waves are very useful in detecting the presence of a different phase which has a large contrast in density. So this graph you need not go into deep, so it is just a variation of velocities with saturation. So the point you need to understand, what you can understand from here is, when there is a large contrast in density parameters, one of the suitable monitoring techniques will be using waves, so which you will be studying. So these are some of the techniques known as geophysical techniques. So some brief was given by professor on MASW, right. So those are shear waves. Here we use both compressional waves and shear waves. and second is resistivity. So brain is a extreme conductor, right, and CO2 is an insulator, right. So what happens when you consider a system and the brain is getting displaced by CO2, what happens? Its resistivity should increase. So that is what we are observing here. So as saturation of CO2 increases, there is a increase in resistivity. So these are some of the techniques, and if you compare these both the techniques, common observation is acoustic velocity techniques are useful in qualitatively detecting the phase, whereas electrical techniques are, you can quantify it accurately. All right. Any doubts? So major question here is, yeah. Yeah. So qualitatively, these techniques are essentially used to determine saturation of the CO2 in the pore space, right. So acoustic velocities are more efficient in detecting that some fluid is getting displaced by some fluid, all right. So with that density contrast, but how much fluid is present, how much second fluid is getting displaced from is displacing the first fluid, that is saturation. So quantitatively to determine that, it is more electrical methods are more suitable. So and here the some of the major questions are, these techniques are highly sensitive to temperatures. So we are experiencing a change in temperature while CO2 is displacing the brine. So the major aspect will be, you will be monitoring that, but you will not understand what is actually happening, whether the change is due to the actual temperature variations, or it is due to the stress state changes, or is it due to the migration of fluid inside. So that part you need to segregate it or differentiate it separately, so that you can get at least you can differentiate those processes. So that is the major research which is being undertaken now. And even from these measurements you can map the distribution of the fluids also. So where it is concentrated, where it is very distributed, so that heterogeneity you can quantify it. So that is also the effectiveness of using it is being considered now. All right, any doubts? Yeah.
We are taking out the brine solution, or we are mixing them both?
Here the major saturation is, it is getting displaced. The fluid is getting displaced. The CO2 will push it as a plug.
So it will push it out of the aquifer?
Yeah. It is not out of the aquifer, it is away from the aquifer. All right. So and as you said, as you rightly mentioned, there is no way out, right. So since it is an infinitely large domain, it will start slowly to push it outside, which is the reason for the increase in pore pressures away from the well or the injection point. So that is where you are getting that response. All right.
So how do we quantify what pore pressure is safe? Let's say we have a limit on how much CO2 we can inject, right?
That
In a particular well, so how do we quantify that?
So that amount of CO2 and first is amount of CO2, that is based on the preliminary estimates on how much pore space is available and what type of mechanisms that take place. All right. And coming to the second question, the rate and this one is based on how the system is expected to behave. So eventually the injection of CO2 is controlled by its injection rate, and for that injection rate how much will be the rise in pore pressure, and this one you need to study it first before getting into it. So that is what the preface of it. Understood? And now determination of saturation is done. So now what happens is that during injection you will be observing some changes in rock properties itself. So there are many susceptible minerals, so which are capable, or in how to put it in a right word is, which are prone to reaction. So when CO2 is injected, so either it can dissolve or it can displace it. When it is dissolving, it forms an acid. So if there are some minerals which are susceptible to reaction with this acid, so there might be some variations, and as well as due to the injection pressure, due to the pore pressure effect, there will be some changes in the petrophysical and geomechanical properties. So petrophysical properties comprises of porosity and permeability. All right. So some tests have been done in this regard. So these are the changes which have been observed with time, as well as some presence of some susceptible minerals which are essentially clays and carbonates, which are relatively quick in reacting with these acids. All right. So this is to give a rough idea how much change is taking place in porosity, and this is for permeability. So and essentially this is for sandstone formations which are relatively inert. So we need not bother about the chemistry aspect of it when it comes to sandstones, which is essentially made of quartz, highly inert, SiO2, silica. All right. So these are some observations. So coming to the next part, geomechanical aspects, which are shear stress, shear strength, elastic modulus, and Poisson's ratio. So this is the simplified phase diagram which exists in the, when you take a REV, representative element volume, if you take some point at any time, these are possible phases that can exist in the reservoir. So one is CO2 and rock, where the brine is getting completely displaced, and second is brine and rock, which is virgin sediments, sedimentary rocks, and third is there, due to the dissolution of CO2 into brine, there will be a CO2 saturated brine form plus rock, and third one is all three will be present in a separate phase. So in this regard, some both UCS and uniaxial tests and triaxial tests have been carried out, and these are the variations of peak stress with different phases. All right. Mostly due to the injection of CO2, there have been observations of minute reduction in peak stresses. So that was the major issue. If the rock stress, one is stress change itself is altering, and one more second thing is the material property itself is getting changed. So this is the second aspect. And this is the variation of elastic modulus, and these things have been published in Journal of Rock Mechanics and Geotechnical Engineering. So if you want, you can go through it. All right. So there will be an elaborate discussion on the techniques which we have discussed. Any doubts till now?
Is there a possibility that the CO2 reacts with the rocks and like escapes out of that?
Yeah. So that depends on the mineralogy of the formations. This is most simplified form. So ideally reservoir would contain faults, and faults would exceed the reservoir extent itself. So in those conditions there might be a chance of leakage, and the fault itself may get reactivated. So it will result in some micro seismic activities. So that, yeah.
And we are also like, after all, we are pressurizing those reservoirs, so we are adding more content.
Yeah.
So if, like in case of an earthquake, like if it gets disrupted, then the whole CO2 will escape out.
Yeah. So those are the things which we need to take care eventually, and to see, now you are asking questions, why? Because you studied this or you got exposed to this. So that is the motto of the at least of my work. Alright. So in order to tackle those, we need to understand these first. And
Why can't we just like remove the brine solution and just put CO2?
so there are some point of views and some very few pilot projects which have conducted this. So, but what is its feasibility, and those things are there. So most of the projects are on existing wells which are depleted oil and gas reservoirs, and very few projects are there in deep saline aquifers which require entirely new infrastructure to be built. So that is the reason people are hesitant about brine extraction. And where will you use the brine? So again, those brine contains heavy metals and things like that which need to be treated again for further uses. So that is an extra cost. So that is why people don't prefer that. Right. Now you understood, that is, we have seen what is happening, and now we will enter into what is actually occurring in the pores. Right. So first interaction is dissolution of CO2 into brine. Alright. So you consider this as CO2 is a solute and brine is a solvent, right? So when you pressurize it at a very high, when you inject at a very high pressure, what happens, what tends to happen? The gas or the supercritical fluid has to dissolve into the solvent phase, which is brine. So the amount of CO2 which is getting dissolved is quantified by solubility, which you are aware. It is basic 10 plus physics or chemistry. So this is the variation of solubility with pressure and temperature conditions, right? So as pressure increases, the amount of CO2 getting dissolved is increased. Which law governs it? Pressure and concentration. Henry's law. Henry's law, which is concentration is directly proportional to the partial pressure, right? So here there is no partial pressure, it is purely CO2 pressure. This is with salinity, and with temperature what tends to happen? Solubility will tend to decrease, right, due to the thermal excitation. And with addition of salt also the solubility tends to decrease. So here solubility is not the rate of dissolution that occurs, it is the final amount of CO2 that is getting dissolved. So this is, pressure is governed, the effect of pressure is governed by Henry's law, and temperature is due to the reduced attractive forces between water molecules and CO2 and salt content, and salinity of brine, those aspects are governed by salting out effect. So when you introduce a new component, so the tendency of brine is that the water will hold more, is more attracted towards the salt phase, ionic phase more than the gas phase. So that is the reason the amount of CO2 getting dissolved is getting reduced. So that is the effect of salinity here. So eventually these interactions are governed by the in situ environmental conditions. So here you can get another aspect of environmental geotechnology or geotechniques, which is how the environment is affecting the geotechniques. Earlier you learnt how geotechniques is affecting the environment. Now we are in the second aspect. Environment is pressure, temperature and surrounding conditions, and which are eventually affecting the geomechanics of the system. All right. So first we have seen, now we have seen amount of gas that is getting dissolved, and second is the rate of dissolution, which is governed by diffusion coefficient. So these are some of the transport phenomena. So diffusion is due to what? Diffusion is due to concentration gradient, and advection is due to pressure gradient, right? So it is similar to, so flow of current is due to voltage difference. Here there is a concentration difference. So concentration is indirectly related here to pressure and PV equal to nRT. So pressure is indirectly related to the number of moles, and number of moles is the concentration of the gas. So this is how it is related. So this the law which is governing is known as Fick's law, and these are some of the at least in water, how CO2 is getting diffused, the rate of diffusion which is quantified by diffusion coefficient. All right. So here in some aspects, apart from pure diffusion, there will be an effect of convection also. Convection in the sense not heat convection. So when a gas is dissolved into the brine, there will be an increase in its density. So within the system, it results in a density contrast or density variation, due to which the brine containing CO2 will tend to move downwards, and pure brine will start to come at top. So that is convection. So if that occurs, the diffusion process will be accelerated, which is evident from the graph, n circle graph, and this is with salinity, and this is when we are introducing porous media. All right. So as K is permeability, which is the resistance offered to the flow in one aspect, or if you consider from a fluid point of view, the ease with which a fluid can flow through the porous media. Most of you are aware of permeability concept. So as permeability decreases, the diffusion coefficient also decreases because the tortuous path increases. All right. So, and as you mentioned, now it is plug displacement. So these are some of the governing equations, and this one. So as who are studying soil mechanics are concerned, you have come across permeability, right? And determination of permeability. And what is the major assumption in that? The soil is saturated. Permeability determination tests are soil is saturated, and there is a flow of single phase fluid, that is water. Now what happens when there are two fluids present? Right? How they will flow? What is the effect of flow of one fluid on other? Are you able to visualize it? So those aspects are governed by parameters called as relative permeability and capillary pressures. So these two aspects govern this displacement process, and these are some of the zones which are formed during this process, and these are some of the observations. Right. So, coming to the questions, what needs to be addressed? First is how much pore pressure is getting generated, how to quantify them. Can we develop any, as such there are analytical and numerical techniques to predict the amount of pore pressure that is getting generated, but can we measure it? How can we measure it? That is first question. Second question is why pore pressure is getting generated, what is happening at the pore scale and how to capture it, right? And what is the effect of this interplay? As I said, there is an interplay of thermal, hydro, mechanical, and if there are some minerals which are prone to reaction, chemical also. So this is known as THMC behavior, coupled behavior. So what is the effect of one aspect on another? What is the so that aspect needs to be established in a comprehensive manner. So, and when you are injecting another phase, major alteration which might occur or which might not occur is the nature of wetting, how contact angles changes. So these you might have come across in physics. So you might have come across the capillary rise, which are and surface tension. So what, due to the presence of two fluids, what is the effect on surface tension, contact angles, and eventually that will govern the hydraulic aspect of this process or this entire exercise. Alright, these are some of the major questions which need to be addressed, and people are working on it. So with this, at least this is what I am doing. Alright, so any questions? Any doubts? So thank you. So if you have any queries, you can go through that paper however.